Okay, in this video, I want to talk about something called heat capacity. We're going to use it to do a couple of examples, but this is something that's kind of crucial for us to get across in terms of working thermochemistry problems. Okay. Let's refresh ourselves a little bit here. We can say that remember that heat is all what we're concerned about right now, right? Heat. This is the exchange of thermal energy due to a difference in temperature. Okay. Temperature is a measure of thermal energy, right? This is kinetic energy. Okay. Um, and that heat is the transfer of the thermal energy. So heat is one of the ways that energy is transferred. So when we're talking about measuring the heat, we're talking about measuring the energy transfer between things. Okay. And if we just let the universe do what the universe is going to do, in other words, if you're thinking about being spontaneous, right? We'll talk about spontaneous in Gen Chem 2. Uh, heat should always flow from things that are hot to things that are cold. And this should kind of make sense, right? If you put out your hot cup of coffee on the counter, excuse me, and let it sit, um, it doesn't get hotter, it cools down, right? And it goes, and the heat is going to transfer until until the system and the surroundings are all the same temperature. When that happens, we say we're at thermal equilibrium. Okay. Um, when we're quantifying heat, the way we're going to do this is we're going to measure the change in the temperature. Okay. Our change in temperature is always going to be T final minus T initial. Where did you end up with, and where did you start? Okay. Um, all right. This way, and because if we do it this way, we don't have to worry about the direction that the heat is going. We only have to know what it is because we're always referencing the system. Okay. All right. So always do it this way. All right. Cool, cool, cool. So let's get into thinking about this as we do stuff. All right, heat capacity. Heat capacity is called C. The heat capacity itself is the heat required to change the temperature of something. Okay, this is an extensive property, which is going to mean that it depends on the amount. Okay, when we're using heat capacity, you'll notice amount does not show up in our equation. That's because heat capacity is extensive, and so the amount has to be built into that. Okay. Here's our delta T. Remember, Q is heat. This is our heat capacity. Okay. Um, heat capacity here is going to have units of joules per degree Celsius. Okay. If you want to think about heat capacity kind of quantitatively, get an idea of it here, um, we can think about it as it's how much effect does adding heat have on something to changing the temperature of the object. Okay. So if you have something that has a large heat capacity, it takes a lot of heat to be applied to actually change the temperature. If you have a low heat capacity, it's going to take very little amount of heat to get the same amount of temperature change. Okay. Um, one of the things I remember as a kid is we had metal slides at the park. Okay. Metal slides in the summer get hot, right? Because aluminum, which is what most of those are, has a low heat capacity. And then when I was in high school and college, I started replacing things with plastic slides. And the plastic has a much lower has a much higher heat capacity. So it means that those could take in more energy and more heat before the temperature actually changed. Okay, so they didn't get as hot in the summer. Um, more often, and actually we're going to see two kinds of problems that work with this as we do stuff. But more frequently in chemistry, we use specific heat capacity, which is called S. Okay, this is the heat required to change the temperature of 1 gram of something, or we could have molar heat capacity, which is for 1 mole. Okay, I've lumped them together here because they use the same equation and they work the same way. One is grams and one is moles, so it just depends on what you're doing. Okay, um, in a specific heat capacity or specific heat, you would say that your heat is equal to the mass of whatever you're dealing with, and we'll work through that, times the specific heat times the change in temperature. Okay, all this is the same kind of idea. Remember, this is an intensive property. So if you notice here in our specific heat units, which are joules over grams times degrees C, ah, um, the mass is built into the unit. So this is independent of the amount. So that means we have to figure out and include mass in our equation. Okay. If we look at the molar heat capacity, it's the same idea, right? Q equals moles times the molar heat capacity times delta T. So this would be moles. Okay. The idea will be the same. This is joules per mole times degrees C. And sometimes you see this as kilojoules per mole. Sometimes you see it as kilojoules per gram. It just depends on what's going on. Just pay attention to the units as we're doing this. Both of these are intensive. The equation looks the same, and so you only see one version of this on the information sheet. Just remember that M could be mass or M could be moles, and it depends on what your uh, specific heat is. If this is in terms of grams, then this is mass. If this is in terms of moles, this arrow should be going to here. If this is in terms of moles, then it's going to be the molar heat capacity. Okay, let's work an example. All right, we take a cold block of silver and we're going to hold it in our hand uh, until it reaches body temperature. Okay, and then we want to know how much heat was absorbed by the silver. Okay, these are essentially the two equations you're going to get on the info sheet. We just have to decide which one we want to use to do this. Okay, we're given two temperatures, negative 5.5 for the silver at the beginning and 37 for silver at the end. Okay, and we have a mass here. Just because mass is given doesn't necessarily mean we need specific heat. But if you notice here, I've given us some data, and the data we're given is specific. Ooh, shit, sorry. Go back. The data we're given here is specific heat. And so we're going to use specific heat for this, right? We're going to need that number right there. Okay. So what we're going to figure out is Q equals mass times specific heat times the change in temperature. Okay. How you plug and chug through this is up to you. I like to do delta T separately and then stick it in there just so it looks nicer. So our delta T here, remember, is always T final minus T initial. Our final temperature is 37 Celsius. We're going to subtract from that negative 5.50 Celsius. This 37 should have a 0.0 on it, so we have another significant figure. Okay, there we go. So this means our delta T is 42.5 Celsius. Then we can stick our other information into the equation. The heat involved here is the mass of silver, which was 10.6 grams. The specific heat, which is 0, where did the 2 come from? 0.235 joules over grams times degrees C. And our delta T was 42.5 Celsius. So now we're just multiplying those three things. Notice here our units cancel out, grams on the bottom, Celsius, Celsius. And the only thing we're left with is joules, which is nice. Okay. So when we multiply those things out, we get 105.8675 joules, and we can round that to three significant figures and call it 106 joules. Okay. All right. Let's think about heat transfer for a bit. Okay. Heat transfer, right, can occur in either direction, system into surroundings or surroundings into the system. Okay. What's key here is that they have to be equal and opposite. The first law of thermodynamics requires that this is true. So there are two different ways we can express this. We can always say the Q of the system is equal and opposite of Q of the surroundings. Okay, that works. Or we can say Q of the system plus Q of the surroundings has to equal 0. Both of those things are true. Okay, you can do a little bit of math there and look at it and figure that out. Um, it's easier to use this one because then you don't have to worry about where uh, you don't have to worry about if the heat is negative or if the heat is positive, if it's going or if it's coming at you. Um, you just have to remember that if you do delta T is T final minus T initial, you'll always get that in the right direction because the temperature change will either be positive or negative. Okay, and that'll control whether or not these guys are positive or negative, and then that'll work itself out. So you don't have to think about the sign that way. Okay. Ultimately, when you're done, the answer should have a sign of positive or negative on it, and that should make sense. Thinking about relative to the system, if your answer is positive, that should be into the system, right? That's our endothermic case. And if our answer is negative, this is out of the system, and that's our exothermic case. Okay. All right. Let's work another example. This one's got a little bit more guts to it, but let's figure this out. Okay. So what we've got is a block of hot iron at 45.8 degrees is placed into cold water at 4.50 degrees. What is the final temperature of the mixture? This is going to be after thermal equilibrium has happened. So let me add that in here so we have it. I don't know why I didn't type it in there, but let's say at thermal equilibrium. Okay. Remembering then our condition here at thermal equilibrium, um, the temperature of the iron has to be equal to the temperature of the water. And this is our final temperature. So this is kind of our condition when we're at thermal equilibrium, that's what's going to happen. Okay. Um, sometimes it's helpful to draw a sketch. We can draw a sketch here. Okay. So let's say we have a beaker, and in this beaker is cold water, right? We have cold water. And we have a hot chunk of iron. I don't know why I felt like drawing this, but I usually draw this on the board so you guys can have it here too, right? We have our chunk of iron, and the iron gets put into the water, okay? When it's put in the water, the hot iron transfers its heat into the water. So what's going to happen is the iron temperature should go down and the water temperature should go up until they're both equal at T final. Okay. So how do we set this up? Okay. Well, we said before, right? We have to obey first law, right? All the heat that came out of the iron went into the water. And so we can say that the two Q's added together, Q iron plus Q water, has to be equal to 0, right? We're going to let delta T figure that out for us as we go, okay? Remembering that delta T is always going to be T final minus T initial. And here, remember that T final is the same for water and for iron, okay? So when I set this up, okay, we're going to use this, and this is how I'm going to do it. Okay, we're going to label everything so we know what's what. Mass of iron times specific heat of iron times T final, which is the same for both, minus T initial for iron, plus mass of water times specific heat for water times T final, which is the same for both, minus T initial for water equals 0. Okay. The only thing we don't know here is T final. Okay, so our job here is to solve for T final. This is our answer. Okay, it shows up twice, so we're going to have kind of an algebra issue here as we do this, but I'm going to work us through it so that we can see it. Okay, um, if you're good with the variables, you can do that. This is one of those times where I think it's a little bit easier to put numbers in there, so we're going to put numbers in here and then work our way through it. Okay, all right. So what do we have? 42.5 grams for iron times 0.449 joules over grams degree C times the T final we're looking for minus T initial iron is 45.8 Celsius. Noticing we've written these numbers from here. There's our iron number. Okay. To this, we're going to add mass of water. I didn't give you either of these masses in the problem. I just realized that. But I'm giving them to you now in the data. I'm sorry, just stabbed me. Okay, 106.3 grams. Okay, specific heat of water, 4.18 joules over grams degree C times we have a T final minus our T initial for water, which was 5.40 Celsius. All that is equal to 0. Okay. There's a lot going on. We're solving for T final. Okay. All right. In the next step, what I'm going to do is I'm going to multiply these two guys and I'm going to multiply these two guys. Okay. So 42.5 times 0.449 turns out to be 19.0825. The grams have canceled. This is just joules per Celsius. We didn't do anything here yet. So I'm just copying this down. Okay. Then we're going to multiply 106.3 times 4.18. That's going to give us 444.334. Again, grams cancels. That gives us joules per Celsius. And our T final minus 5.40 Celsius equals 0 is all still there. Okay. Now what I'm going to do is I'm going to multiply and distribute this into here and this one into here. Okay. This is going to, I know it sounds like a lot, but this is the step that makes everything work out. Okay. So we end up with 19.0825 joules over Celsius times our T final minus 45.8 Celsius times our 19 point whatever. And this is 873.9785 joules. The Celsius on that part cancels out. Okay, the units matter. Okay, again, we're going to have 444.334 joules over Celsius times our final temperature minus 540 times 444, 2399.4036. The Celsius canceled out, that's joules, and this is still equal to 0. Okay. Next, we're going to combine our like terms together. Remember doing that in the algebra class? Okay, we're going to do that here. We have these have T final in them, and these ones don't. So that's what we're going to combine together. This plus that, oh, excuse me, is going to give us 463.4165 joules over Celsius times T final. And then we're going to have minus 873 minus 2399 gives us minus 3273.3821 joules. And that whole thing is equal to 0. Okay. Then we're going to move the one that doesn't have the variable with it. Remember, we're solving for T final. Okay. So we're going to move the other guy to the other side. So this is coming over there, which means we're going to flip the sign for it. 463.4165 joules over Celsius times our final temperature equals 3273.3821 joules. Okay. Then our last step is to get our T final by itself, and we'll do that by dividing by this number on both sides. Um, that'll give us to say that T final is 7.0636 Celsius. And for three significant figures, we'll call that 7.06 Celsius. Okay. So the iron cooled down dramatically, the water warmed up a little bit, and there we have it. That's a big problem, but once you set it up, the chemistry part is setting it up. The rest of it is algebra, and we should be able to do that. All right. Let me know if you have questions, and I'll catch you next time.